Now, after defining analysis and synthesis, we are ready to define signal analysis and signal synthesis. So let's start with signal analysis. As we discussed earlier, analysis is the process of splitting or breaking or decomposing some complicated looking quantity into the simpler one. Now, by keeping that concept of analysis in our mind, we can define signal analysis as a process which splits or breaks or decomposes a given non-sinusoidal signal into the number of sinusoidal signals. This is the definition of signal analysis. Now, why we are considering non-sinusoidal signals as the complicated one and sinusoidal signals as the simpler one? As we already know, there could be infinite possible shapes of non-sinusoidal signal. It could be a square wave, triangular wave, sawtooth wave, rectangular pulse train signal, or any arbitrary signal. So whatever the shape of a given non-sinusoidal signal, it will be treated as the complicated one because it can be simplified or it can be represented in the form of pure sinusoids. And each sinusoid will have its own unique frequency value. As we discussed in the example of white light analysis, each component color of a white light will have its own unique properties. Similarly, every sinusoidal ingredient will have its own unique frequency value because frequency is the parameter which makes a given sinusoidal signal different from the other one. So, what is the main objective or goal of performing signal analysis? We want to represent any real world signal information at the ingredient level or at the basic building block level. And while performing signal analysis, we have to find two things. What particular sinusoidal signals or what particular sinusoidal components are present in a given non-sinusoidal signal. This is the first main objective. And the other main objective is we have to find their contributions. Or in other words, we have to find the exact quantity or proportion or the contribution of a given sinusoidal signal in a non-sinusoidal signal. So this is the main objective of signal analysis. Now to discuss signal analysis in more detail, let's take an example of a given non-sinusoidal signal which has some arbitrary shape for which we want to write its mathematical expression. So we are required to develop a mathematical expression of this signal. Can we develop a mathematical model of this signal by just looking at it? The answer is it's very hard to express it mathematically because we do not know what particular frequency components are present in a given signal. Secondly, we also do not know what is the exact contribution of those sinusoidal components. So if we want to develop a mathematical expression of this signal, we can do it by performing its analysis. If somehow we analyze our signal and express it in the form of sinusoidal components, then we can express it mathematically because we already know the mathematical model of a sinusoidal signal. It has three parameters. It has some amplitude, some frequency value, and a phase value. So let's assume we analyze our signal through a tool which tells us our signal contains three sinusoidal components of 1 Hz, 2 Hz, and 3 Hz, and the corresponding amplitude values are 2, 1, and half respectively. So after knowing that the given non-sinusoidal signal is simply a composition of these sinusoids, now we can write a mathematical expression of this signal, this non-sinusoidal signal, in terms of sinusoidal signal very easily. So the components or the ingredients of the given arbitrary wave are these sinusoids. Here we have used a small b to represent the amplitude or the quantity of a sine wave, and a small a is representing the amplitude of a cosine wave, and the subscript value is actually representing the harmonic number. B1 is actually representing the amplitude of fundamental sine wave, and A2 is representing the amplitude of second harmonic cosine wave, because the frequency value of this ingredient is twice of the fundamental component, and A3 is representing the amplitude of the third harmonic component or third harmonic cosine wave. Why this waveform is the third harmonic? Because its frequency value is 3 times of the fundamental component. And why we are considering this component as the fundamental one? Because if you look at the time period value of the resultant signal closely, its time period value is 1 second, and this signal is also completing its one cycle over the 1 second interval. So the green color sine wave is actually the fundamental component of the given non-sinusoidal signal, and this blue color cosine wave is the second harmonic component, and the purple color cosine wave is the third harmonic component present in the given signal. So we can simply write x of t, or a non-sinusoidal signal, is equal to summation of these sinusoids having the amplitude values of 2, 1 and half, and the frequency value equal to 1 Hz, 2 Hz and 3 Hz. And since all sine wave, all these sinusoids are starting from their initial position, so the phase value is 0. So we can simply write b1 sin omega t plus a2 cos 2 omega t plus a3 cos 3 omega t. If these sinusoids will be somehow shifted over the time axis, then we can introduce that phase value in these expressions as well. So this is the way to express any real world non-sinusoidal signal in terms of sinusoids. Now let's come to signal synthesis. As you already know, synthesis is a process of adding two or more simpler quantities in order to produce the desired complicated quantity. Similarly, signal synthesis is a process of adding various simple sine waves in order to produce the desired non-sinusoidal signal. As we discussed in color synthesis example, by changing the contribution of primary colors red, green and blue, we can create a variety of colors. In a very similar manner, by changing the contribution or quantity of simple sine waves, we can create any desired non-sinusoidal signal. So the conclusion is very simple. Any real world non-sinusoidal signal can be synthesized in terms of simple sinusoidal signals. This is the basic idea of signal synthesis. Here you can see 7 simple ingredients which we are going to add together, or we are going to synthesize together in order to get this one. And the list of ingredients includes fundamental cosine wave having an amplitude A1, fundamental sine wave having an amplitude B1, second harmonic cosine wave having an amplitude A2, second harmonic sine wave having an amplitude B2, the third harmonic cosine wave having an amplitude A3, the third harmonic sine component having an amplitude B3, and finally the DC signal having an amplitude A0. So after combining all these 7 simple ingredients, the resultant quantity will be a complicated looking non-sinusoidal signal. One important thing which you should remember is, on adding just sine and cosine waves, the resultant signal's shape will be exactly similar to this one. In other words, if we will not add the DC signal in this example, then the resultant signal's shape will be exactly similar to this one, but the only difference will be that that particular signal will be completely symmetrical around the x-axis, which will show its averaging value is 0, because if you will just add some sine waves and some cosine waves and obtain the resultant signal, then its averaging value will be 0, because if you observe the averaging value of these sine and cosine waves, it's also 0. So the properties of the resultant signal are depending on what ingredients we have added together. So if you will add DC signal in addition to these sine and cosine waves, then the resultant signal will be look like this one, which is not symmetrical around the x-axis, which is an indication of this signal is symmetrical around some other value. And that particular value is actually A naught in this case, because this signal contains a DC offset of A naught value. So the conclusion is very simple. Sine and cosine waves actually defines the shape of our signal, how the resultant signal will vary itself, and at what particular axis our resultant signal will be symmetrical. It depends on the DC value. So if our signal does not contain the DC component, then the resultant signal will be symmetrical, otherwise not. So you can consider DC, cosine wave and sine wave as the basic ingredients of any real-world non-sinusoidal signal. This is the basic idea of signal synthesis. Now, in order to conclude this discussion, both signal analysis and signal synthesis are presented on a single slide. So if this signal is given to us, then this representation will be considered as the complicated one, because by just looking at this waveform, we cannot answer whether a 1 Hz, 2 Hz, 3 Hz, 7 Hz, 10 Hz components are present in it or not. So firstly, we will need to split the given non-sinusoidal signal into the sinusoidal signals with the help of a certain tool. And in this case, Fourier will be the relevant tool. So by applying Fourier on a given signal, we can have these sinusoidal components, where each sinusoidal signal will have its own unique frequency value. So this was the signal analysis. Now, signal synthesis is totally opposite to signal analysis. If these sinusoidal components are given to us and we are asked to find the resultant signal after combining these sinusoidal components, then what we can do, we can apply inverse Fourier on these sinusoidal components. Inverse Fourier will just combine, or the synthesis equation of Fourier will combine these sinusoidal components in order to provide the resultant signal. So analysis and synthesis equations are, or analysis and synthesis process are transform pairs of each other.